So we're looking at implicit differentiation. So we've got lots of little bits of different differentiation that can make it up. Remember, we're in that merit zone at the moment. So implicit differentiation was invented because of a certain type of graph. So can anybody tell me what this looks like? Can anybody tell me what that looks like? It is a circle. Now, the problem with a circle and lots of other graphs is that they are not functions. To be a function, there's only ever one value of y associated with an x value. But it still is a graph. So this would be a graph with center 0, radius 3. All right? So if I wanted to find the gradient at some particular point, I would pick a point, find the gradient. But the problem is that at that point on x, there's actually 2 points. So to designate that one, I need to be able to designate the y point as well. So that brings us to a problem. To find the gradient at that point, I need to differentiate and find the gradient function, right? So, have a little problem here. I've got y's and x's in this. So I could rewrite this. I could write it as y equals the square root of 9 minus x squared. Right, that's fine. I can rewrite that. And now I could use the chain rule and differentiate that. But I'm not going to, because that is not what we're learning today. I could do that. Oh, I would probably need a plus and a minus here to get those both sides of the line. So if we were going to do this with, I'm going to make it a different one just so we don't get confused. Y squared plus x squared equals 25. I have a circle. I want the gradient at the point, no, I'm not even going to ask for the gradient. What is the equation of the tangent at 3, -4. All right. So I know 3, -4 is on this graph because this particular circle has a radius of 5 and it's a 3, 4, 5 triangle. So I can figure that out in my head. Yay, go me. So what I want to do is I want to be able to differentiate this equation without rewriting it. So what does dy by dx mean? Right, differentiated the y with respect to the x. But it also means that I have actually differentiated y. So if I was differentiating y, so in this case, that y changes to this. Now the trouble here is that this y, I've not got any x's in it. So I need to differentiate this y. I can differentiate the rest of it, but this y, I can't differentiate in that same way. So what do I need to do? Okay, got this dy by dx, which is what I want to find. That's my gradient function. I'm going to split this up into x's and y's. So yesterday we learnt that we can differentiate with different things, all right? We can differentiate y's with respect to t. We can differentiate x's with respect to y, etc., etc. So we just have to figure this out. So in this, what we're going to do here is we're going to differentiate this with respect to y. We're going to get 2y differentiating y with respect to x. Now, if I'm differentiating this for all the x's in it, what am I going to get? 0, because there aren't any x's in it. Whoa. So this one, if I'm differentiating this as per normal, dy by dx, what will this equal? 2x. And if I differentiate this by all the y's in it, how many y's are in it?
0.
Right. And this one, if I differentiate this, I get 0. So this is what we've ended up with here. So now I want to have dy by dx. That's my gradient function. So I'm going to take everything else over here. I'm going to get 2y dy by dx equals negative 2x. Therefore, dy by dx is equal to negative 2x over 2y. Right? All the zeros just went away. This is my gradient function. So therefore, at 3, negative 4, the gradient will equal negative 6 over negative 8. 3/4. Happy with that? Okay. So now to find the tangent, I need a point. Well, they nicely gave me one. All right. Y minus plus 4 equals 3/4 x minus 3. That would be my equation of the line. Nicely rewritten. What rewritten equals 3/4 of x minus 9 over 4 minus 4. Minus 9 over 4, which is 2, minus another 4, minus 6 1/4, I think. What do you reckon? That times that is negative 9 over 4, which is negative 2 1/4, minus another 4 is negative 6 1/4. So that's my equation of the gradient. So if we had a look at this, so we're talking about, let's pretend this is the one with a 5. 3, negative 4 would have been down here somewhere. I'll just cheat. So 3, negative 4 is going to be approximately here. Yes, the gradient is obviously going to be positive, all right? And it's going to go through at a negative point lower than 5. Can you see that? So if this picture was this circle, would have a radius of 5 and negative 5. That point is approximately here. The gradient at that point would get some sort of slope going on here. It's 3 up, 4 across. It's definitely more across than it is up. And it's gone through the y-axis at approximately, well, exactly actually, negative 6 1/4. Okay, so that could have been done a completely different way. But what if it can't be done a completely different way? Let's have a look at this one. Now, I have no idea what this looked like, but luckily in the textbook they drew it for me. So this looks like this. There you go, that's what that looks like. That's what that function is. It's not a function because I can put my hand on here and it's got 2 values. That makes finding the gradient more difficult because we need to know what the y position is as well as the x position if we're detailing one particular point. With a function, if they give you the x, there's only one y value, so we can use that x to find out what the gradient is. So, if we were going to do this one, we have to implicitly differentiate it. I would not want you to try and rewrite this in terms of y because it would probably take you half the exam to do so. So we're not going to do that. We're going to learn to do this. So what this says is we split it in all its little bits. So we're going to have 1 in terms of x, 1 in terms of y, 1 in terms of x, 1 in terms of y, and the same here, but these are both going to be 0 because that's a number. All right? But these ones here, when we are differentiating with respect to x, we treat y as a constant. So this one is going to differentiate to, Good, 4xy. That's with respect to the x's in it. Now, if we, with respect to the y's in it, we're going to differentiate. Now the x's are a constant. So what's going to happen?
2x squared.
Okay, 2x squared, but this time we have to add this thing because we weren't doing the normal. All right? So now we do the next one. In terms of y, in terms of x, sorry, we will get 3y squared. In terms of the x's, we will get, sorry, the y's, we will get 6xy and the dy by the x, and it will equal 0. Now we have to rewrite it. We need to rewrite it as dy by dx equals. So according to our algebra, that means we take all the dy's by the x's on this side, stick everything else on the other side first. So we're going to get 2x squared dy by dx, a 6xy dy by dx equals a negative 4xy and a negative 3y squared. Happy? Okay. Now, we're going to take, we only want one dy by dx, so we're going to take it out as a common factor. That leaves us with a 2x squared and a 6xy over here. Now we've only got one of them. And this lovely thing over here. Next, we are going to divide. Good. Dy by dx, which is what we're after, the gradient function equals this thing over this thing. So, if they wanted us to find a gradient at a point, they would have to give us a value. So I know that this point here is 1, 2. All right? So if I want the gradient, what is the gradient going to be, positive or negative? Negative. Okay, so we want a negative answer. So at 1, 2, we're going to get the gradient, dy by dx, equals, negative 4 times 1 times 2, negative 8, minus 2 squared is 4 and 3 makes 12, yes, over 2 1 squared is 2, plus 6 times 1 times 2, 12, so that equals negative 20 over 14. Definitely a negative gradient. Happy with that. Not even going to change it. Are we happy? Do we see how it works? Everything when we have x's and y's in the original equation, every term, x, y, x, y. Collect all the dy by dx's, chuck everything else on the other side, and then divide by that common factor bracket. Okay?